So let's start with the basics. Let's say you have some sort of Java code. You'll first compile it to bytecode using this tool of Java C. And this bytecode is an intermediate representation of your code, which provides a portability wherein you can run the same bytecode across different kind of architectures. So you can use it on Intel, which is x86 architecture. You can run it on ARM, and you have some other architectures like Spark, Power 9, and so on and so forth. So when you really run this bytecode, when your application runs on the JVM will convert your bytecode into the machine code. And this step is also called compilation. So in this video, we'll focus on this compilation and not the conversion from Java code into the bytecode. So when your application starts, now the application has access to the bytecode. It will go one line at a time. It will use some sort of dictionary which tells it that, okay, you are running on x86 architecture, which is an Intel or an AMD chip. And for this kind of bytecode, you need to convert it to this kind of machine instruction. So there is a component within the JVM called interpreter, which will go through the bytecode one line at a time. And using this dictionary, it will convert your bytecode into the machine instructions. And it will send those instructions for the CPU to execute. And that is how your application starts running. So interpreter is very quick to start your application. It doesn't waste time in compiling your code, converting each line of your bytecode repeatedly into the machine code, even for the repeated code snippets like the for loop or the methods that you're calling again and again. It's very inefficient. So JVM keeps a performance counter for which methods or which snippets of code are actually executed how many times. For example, if there is a method called add and it is repeatedly called, the counter of how many times that method is called will be incremented. Once that counter reaches a particular threshold, let's say this method add is run 10,000 times from the point where your application started. So that means this method is going to be used a lot more times since it's already used 10,000 times. So it's better that we compile it and save the compiled copy once. And while we are at it, let's optimize the code a little so that the compiled code runs faster than the interpreted code. And that's the job of this compiler called the C1 compiler. The C1 compiler will take the snippets of code which have been run 10,000 times by the interpreter. It will compile it, it will optimize it, and it will save that compiled machine instruction into this area of the JVM called code cache. So the next time this method is called, instead of the interpreter doing the conversion, we will pick up the compiled code, the optimized code from the code cache and give those machine instructions to the CPU to run. So now that part of your code has become faster. Also, choosing this performance counter a threshold of 10,000 has certain trade-offs. So if you keep this counter too low, let's say the counter is only 10, every time a method is run or a snippet of code is run only 10 times, we will use the C1 compiler and will optimize the code. The problem is your code cache is very small. It is only 240 MB. So even if the parts of the code which are used very infrequently, even they will be optimized, and you will be spending a lot of CPU and resources in optimizing that code. And this 240 MB of code cache will be filled very quickly. So now the bytecode is being interpreted and the methods which are used frequently are compiled and they are used from the code cache. And your application keeps running for a while, and in the background JVM will start collecting the runtime statistics of how your code is being executed, and this is also called code profiling. And it will try to create control flow graphs or code paths of your code. So it will find the hottest paths of your code which is always executed. Once it has enough statistics that yes, this is the control flow, this is the code path that is always used in the application, it will ask this other compiler, which is C2 compiler, to perform even heavier optimizations on that part of the code. C2 compiler will perform heavier optimizations, and all the corresponding compiled code or the machine instruction, just like the C1, it will also keep it in the code cache. If the same method was compiled by C1, it will replace that C1 method's machine instructions based on its own output. In Java 7 and before, we could choose which compiler do we want. Do we want the client compiler, which is the C1, or do we want the server compiler, which is the C2? C1, as we spoke about, doesn't consume too many resources. It is faster to compile, but it does less optimizations. And C2 compiler is opposite. It is slower, it is more resource hungry, but it will do heavier optimizations and it will create faster code. So for GUI applications, C1 was used, and for server, which is the long running applications, C2 was used. But in Java 7, there was an option to choose both of them together, and in Java 8, that became the default behavior. So now we have both the compilers running simultaneously for the code. Initially, the code will be interpreted. If it reaches a certain threshold of 10,000, it is compiled by C1. And if based on the runtime statistics or the code profiling, the code requires even heavier optimizations, then C2 compiler is called, and it will compile it and optimize it in a even better fashion. What exactly are the optimizations which are done by C1 and C2? So first one is dead code. So if there is some part of your code which is not executed at all or not used at all, some unused variables, they are removed from the compilation. Second is escape analysis, where if there are any objects created within the method and they are never returned, then they are assigned to the stack rather than assigning it to the heap, so that garbage collection can be faster. And these are only a subset of all the optimizations. There are at least 20 more, and this whole flow of profiling the code, finding hot parts of the code which are most frequently used, and only compiling them and only optimizing them further is the very reason that the Oracle's VM is called Hotspot VM. The C1 and C2 compilers, they do not stop the application from running. So based on the number of cores, it will decide how many background threads to create for both C1 and C2. And while the code is being interpreted, behind the scenes, the compilation can go on. And once the compile code is ready, the VM will execute the code from the code cache instead of asking the interpreter to do it. So all these compilations and interpretations is being done at the runtime. So while your application has started and is running, only then you are doing the compilation. And that is why the name just in time compilation. Now the question is, can we not do it ahead of time? Can we not do it while we are converting our code into bytecode? And that is called ahead of time compilation. So from Java 9, we have this option of converting some of your code or some of your libraries into the compiled code before even you run the application. So just like Java C, we have this executable which will convert your bytecode. So in this case, we are converting the hello world.class into this compiled code called libhelloworld.so. And then whenever you want to run any of your classes, then you have to pass in this library which you just compiled using this switch. So in the first slide, we saw how the code is converted into bytecode first. But now we have encountered one problem. Our bytecode is portable. It can run across multiple architectures. But when you compile it, that means you're converting your bytecode into the machine instructions of a particular architecture. So how can this compiled library be cross-platform? And the answer is it cannot be. And as of Java 9, Java only supports architecture called x86. So your compiled library will run only on this architecture. So now our runtime changes a little bit. Anything which is loaded as a bytecode will continue to run as is. So it will have interpreter, it will have C1 and it will have C2. And any of the compiled libraries that you loaded, that will be directly added to your code cache. So now you can skip the interpretation and the C1 compilation for parts of the code which are present in the library. So that's a summary. We use bytecode so that it's portable across architectures. The code is initially interpreted line by line, and then after some threshold of 10,000 times of execution, it is converted into machine code. Based on some runtime analysis or code profiling, the code is further optimized by the C2 compiler. And if we choose, we can use AOT compilation for some of our code or some of our libraries to avoid doing this interpretation and C1 compiler job and start our application even faster. And all of this compiled code is stored in code cache, which as of Java 8 is of 240 MB. That's it for this video. Thanks a lot for watching and see you in the next one. Bye.